Hello everyone, welcome to our class on basic electronic circuits. The topic for today is junction field effect transistor, construction, working and characteristics. So let's move ahead. So this is basically the structure of a junction field effect transistor. You can see there's going to be one block of a semiconductor. It could be either a p-type or an n-type. On the sides there going to be an other type of a semiconductor material doped in. These materials that are shown by a pink color are connected internally, which forms the gate terminal, and the other two terminals form source and drain. Now, since they are going to be of different dopings, you will have a junction form the moment they are connected. So the moment they are connected, you will have a junction form. This is mainly due to the diffusion of charge carriers through the junction, and that is why you have a PN junction created there. This depends upon the doping densities that are present between the p-type and n-type. Now let's talk about the biasing that we apply to this device. So when I have a junction field effect transistor, I'll be applying a reverse bias between gate and source, and I'll be applying a forward bias between, or I'll be applying a more potential at the drain and less potential at the source. So the moment that happens, I'll have charge carriers traveling from source to drain, and I'll have a current setup. The positive plate at the battery is going to allow more number of electrons in this case to be absorbed, and hence I'll have a current flow from my drain terminal to the source terminal, because the conventional flow of current is opposite to that of the electrons. Now let's discuss mainly about the VGA's battery, because it is the one that plays an important role in the control of the current ID. As you can see, the biasing applied at the gate is the reverse bias. This reverse bias helps me to control the width of the channel. So if I increase the reverse bias, I'll have an increased depletion region. Note that the depletion region is more towards the drain side and less towards the source side, because drain is more positive as compared to source. Now, as I have increased my VGS, the effective channel width has reduced, and so number of charge carriers that can travel from source to drain will reduce. If I go on increasing it, what is going to happen is my effective channel width goes on decreasing. So by controlling the voltage at VGS, I can control the current that flows from drain to source, or in other words, I can control the number of charge carriers that can move from source to drain. If I increase my VGS further, there will be a point where the channel width becomes 0, and hence there will be no charge carriers traveling from my source to drain, and my current ID becomes 0. This is when I call my channel has got pinched off and my current becomes 0. This point is when I have applied maximum VGS. This voltage is also termed as VP, pinch off voltage. The current when my VGS is minimum, or when my VGS is equal to 0, is called as IDSS, and it is the maximum current that can flow through any device. Also note that as my VGS changes, my current ID changes. So in this case, junction field effect transistor is nothing but a voltage control device. This same characteristics can be seen when I have a p-channel JFET. So now the charge carriers that will be traveling will be holes between source and drain, and the biasing that will be applied will be exactly opposite. So my VGS is going to be positive and my VDS is going to be negative. Now let's move away and talk about the symbol for JFET. So junction field effect transistor, as we've just studied, can be of two types, one which is n-channel JFET, the other which is p-channel JFET. So there are three terminals: gate, drain and source, as you can see in the symbol. The gate terminal was always reverse bias for effective control of current ID, and since it is reverse bias, there is no current IG flowing. In fact, current IG is going to be equal to 0. So the arrow in the symbol does not indicate the current flow, but it indicates the junction form. So when I have an n-channel JFET, the gate is positive and my channel is negative, so the symbol indicates the PN junction form in both the cases, N channel and P channel JFET. Let me move to the 6th of junction field effect transistor. Unlike BJT, we don't discuss input and output characteristics, but we will be discussing the transfer characteristics and the output characteristics. The reason is my input current for JFET, that is current IG, is equal to 0 as my input junction has reverse bias. Let's start off with our transfer characteristics. So the graph on the left hand side is my transfer characteristics, where I'm plotting my change in ID with change in VGS. So as you can see, the graph is going to be parabolic. When my VGS is equal to 0, that is on the y-axis, I can see that there is a maximum current flowing, which is my current IDSS. And when my ID is equal to 0, that is my VGS is going to be maximum negative. I have a point which is pinch off. That is when my channel has got pinched off and I have no current flowing through my channel. This characteristics gives me a slope which is going to be called as GM, and GM is nothing but change in your ID due to change in VGS. Now let's move on to the graph on the right hand side, which is my output characteristics. As you can see, the graph is divided into three parts: cutoff, saturation, and ohmic. Cutoff is when my VGS values are quite negative. They are very close to pinch off voltage, and hence my current ID is going to be equal to 0. Ohmic region is the region when I have my current ID varying linearly with VDS. That is when my VDS is less than VGS minus VP point. So I call it to be in linear region when my VDS is less than VGS minus VP. When my VDS is greater than VGS minus VP, VDS has very little control on current ID and you have almost straight curve. The characteristics are very much similar to my BJT in common emitter mode. I can also find out my output resistance RO, which is inverse of the slope of output characteristics. RO, or internal resistance RD, can be given as 1 upon change in ID due to change in VDS. Talk about various characteristic equation in JFET. The first being ID equal to IDSS in a bracket 1 minus VGS by VP, the whole square. Next is when I have GM equal to change in ID with change in VDS, change in VGS with change in ID. Then I have my output resistance, which is inverse of change in ID with change in VDS. Then I have intrinsic gain mu, which is nothing but multiplication of GM, which is my transconductance, into my output resistance RO. GM can also be found out to be equal to GMO in a bracket 1 minus VGS by VP. I can find out GMO to be equal to twice IDSS upon mod of VP. Now let's also talk about JFET characteristics when the JFET is in linear region or ohmic region. The equation is given by ID equal to area upon L into conductivity into VDS. So my ID can be found out as conductance into VDS, where conductance is given by A, which is nothing but B into W, that is your thickness of the channel into width of the channel, upon L, which is nothing but channel length, into conductivity, which is Q into ND into mu N, where Q is nothing but electron charge, ND is the doping concentration, and mu N is the mobility of my charge carrier. Here in this case it is mobility of my electrons, multiplied by my VDS gives me ID. Now that is about my current ID when it is in the linear region. Thank you.